So this is a talk about distributed systems and ONOS with Atomix. So over the last couple releases, there have been, well, probably the last 2 or 3 releases, there have been big changes to some of the architecture of ONOS, and this is sort of a guide to what exactly was done and why it was done. So this talk is going to be separated into 4 parts. So just a brief architecture review of what the cluster was like prior to the architecture changes, what some of the problems were to that and the proposed solutions, and then discussion of Atomix 3, basically the project that came out of the architecture changes, and then how it fits into the new ONOS cluster architecture. Yeah, so the pre-OWL, so the OWL is the name of the 1.14 release. So, yeah. So prior to the 1.14 release, the ONOS cluster just looks something like this. So you just have some set of nodes, switches connect to them. I don't know what happened to my color on these things. Yeah, and so essentially on the nodes, we elect masters, which basically dictate which controller node is controlling which switch, and then the switches connect to them. And then on the controller nodes themselves, there are a variety of different protocols running. Some protocols for the southbound state, eventually consistent protocols, some Raft partitions and things like that, like I talked about earlier, and I'll talk about that a bit. So the ONOS cluster typically consisted of an odd number of nodes. 3 or 5 or 7 nodes. NetE is used for east-west communication. A lot of the stores, the stores are mostly written 2 ways. A lot of the stores use consistent primitives for persistence and replication, and a lot of them use, the ones that don't typically use either one eventually consistent primitive or a custom eventually consistent protocol. And then, so yeah, distributed primitives sort of provide a high-level interface modeled as collections and concurrency primitives to interacting with various distributed systems protocols, and then stores are either built on those or custom protocols. So this is sort of an example of what a store might look like in ONOS with a distributed primitive. So this is taken from the route store, which just creates this consistent multi-map primitive and then adds routes to it. And behind the scenes, there's all kinds of distributed systems protocols happening. But what were the problems that we ran into with this? So one of the big problems is with embedding Raft in general. And the problem is that Raft, because it's a consensus algorithm, consensus algorithms have really strict configuration requirements. And this was the cause of ONOS having really like fixed cluster configurations, where in cluster.json you have to define the set of nodes in the cluster, and you have to define the partitions and things like that, because if they're not defined ahead of time, then you can run into consistency issues. And then obviously running consensus on the controller also affects the availability, because consensus algorithms like Raft require a majority of the cluster to be available to make progress. Embedding an expensive protocol like Raft, or many instances of an expensive protocol like Raft, can affect other portions of the system. If a Raft partition is catching up, and it's in the same process as southbound protocols, you're also affecting those southbound protocols. And then it's proven to be really difficult and expensive to reconfigure or scale the cluster, and sort of buggy. So adding nodes to the cluster, removing nodes, and it's because of Raft partitions. So cluster reconfiguration is built into Raft, but it's still a really complicated process and really expensive. And then, so there's all this cost, but there's not that much benefit to it, because if you think about it, in like a 5-node cluster, Raft is a leader-based protocol, so every operation has to go through a leader. So in a 5-node cluster, 4 out of the 5 nodes still have to send operations to some other node, and so there's still a network in between the nodes most of the time, or in between the nodes and the Raft protocol, I should say. And then there are the distributed primitives. So the notion of distributed primitives has proven really valuable. When we're talking about future ONOS or next generation ONOS, people have brought up that they really like them and want to preserve a way for average developers to interact with distributed stores easily. But the problem is that all the distributed primitives in ONOS have been limited to a single protocol up until now. And so people have come to me in the past and said, hey, can we have like a faster in-memory consistent map or something like that? And I say no, because it implements the Raft Protocol, and you can't just mess with the safety of the Raft Protocol. And then there's the distributed systems code itself. So obviously ONOS, so there's been tons of distributed systems work done in ONOS over the years by me and then Madan before me. And so there's like intra-cluster communication and cluster management, distributed primitives, partitioning, eventually consistent protocols. But the problem with this is that that's all code that's in ONOS and being maintained in ONOS, and nobody else can use it, but it's actually really useful in general code, and both ONOS and other people could benefit from moving it out of there. So what's the solution to these problems? So earlier this year, I don't remember when exactly it was, I went to the TST, the ONOS TST meeting, and proposed that we re-architect the ONOS controller to move the Raft protocol off to other nodes. And that would allow us to scale and upgrade the ONOS controller independently of the storage layer. And then in doing that, I proposed we sort of move a lot of the other distributed systems work into a separate project, as well as the distributed primitives, and then so we could get more users and contributors contributing to the distributed systems code, and then find a way to solve the primitive protocols problems to allow new consistency models and new performance characteristics for primitives. And then, since we're talking about next generation ONOS, we want this project to also be able to support whatever future goals we might have. And so this is sort of what I propose. So basically, rather than the ONOS controller just having a fixed set of symmetric nodes, moving the storage layer off to another cluster, and I'll talk about that a lot later. So work began on this sort of around 1.12 when we started sort of improving the Raft implementation itself, and sort of continued over a couple releases to 1.14, which is the OWL release. So it kind of happened in 4 stages. Migrated the cluster management and communication layers out, built generic interfaces for the distributed systems protocols, migrated the distributed primitives themselves, and then modified the ONOS controller cluster architecture itself. So that brings me to Atomix 3. So Atomix has historically been really just the Raft implementation that's been used in ONOS. So actually, it started out that Copycat was the Raft implementation, and Atomix was sort of a thin layer on it for building primitives, which we used to build primitives. And then those got merged together. But now, a lot of the distributed systems code has been moved out into Atomix, where it can be reused and accessed by other people. So what is Atomix 3 today? So I call Atomix 3 a reactive Java framework for building scalable, fault-tolerant distributed systems. And it provides primitives for every layer of distributed application. So it provides intra-cluster communication, cluster membership, replication, synchronization, or coordination primitives, and fault tolerance mechanisms. So the sort of key tenet to Atomix 3 after this big refactoring effort is that it's unopinionated as to the architecture of clusters, and this is really important for sort of for the long-term evolution of ONOS as well. So in other words, it doesn't prefer a specific cluster architecture, and you'll see what I mean as we get into it. Instead, it just provides options. So for example, it can be used as a library or as a service. It supports synchronous or asynchronous programming models. node roles. It doesn't have node types, but the sort of role of a node in the cluster is defined by its configuration, which we'll look at. Supports different reliability mechanisms for communication, different messaging patterns, and then the primitives or the data structures and concurrency control mechanisms also don't care about the protocol that they run on. So this is what starting an Atomix node looks like. So it's just a Java API that uses the builder pattern, much like a lot of the ONOS code uses. And so by just doing something like this, a few lines, you've created an Atomix node. But what does that mean? Well, the features that are provided by Atomix 3, there's really a small feature set. And that is cluster membership, cluster communication, and distributed primitives, which there's a wide array of distributed primitives, but it's sort of one abstraction. And so let's look at some of these APIs real quick, and then we'll get into them. So for example, cluster membership, and a lot of these APIs will look really, I mean, obviously a lot of this work came from ONOS, so they'll look sort of similar to APIs that are in ONOS. And so the cluster membership service, for example, provides information about the nodes in the cluster. So when an Atomix node is started, other nodes are notified about it. And so yeah, this is like showing an event notification which is received, and it looks a lot like ONOS code, which notifies a node when another member is added or removed from the cluster. And so the cluster membership service is responsible for joining a cluster, locating members, and detecting failures. And one of the cool properties of it is that, well, you can assign properties to members of the cluster. And this is one of the features that allows a system like ONOS to differentiate between different types of nodes, because as we'll see later, ONOS needs to be able to differentiate between which nodes are the ONOS controller nodes and which nodes are the Atomix nodes. And then there's cluster communication. Again, this looks very similar to what's in ONOS. So it's based on Net-E4. It's asynchronous APIs and supports a variety of messaging paradigms. Again, request, reply, publish, subscribe, reliable and unreliable, etc. So there are two primary interfaces for communication in Atomix. And the reason there are two is because they're for two different types of systems, really. So the Cluster Communication Service, so this is actually a name that's taken from ONOS, is just like the one that's in ONOS, where it's used for a node to send a message to another specific node or to a specific set of nodes. And it supports, again, different patterns: request, reply, unicast, multicast, broadcast. So the alternative to this is an API that's designed for service-oriented architecture. So rather than sending messages, from point A to point B, or to looking up a specific node in the cluster and sending it a message, you're actually just sending messages to topics, and those are load balanced. So there's load balancing logic built into it that's just round robin. And so this is like sort of a publish subscribe messaging for everything. And so again, this is the APIs here look very similar to what exists in ONOS, right? So the Cluster Communication Service, you just create a reference to a member ID, which has a string name, and you can send a message to another node. And then there are distributed primitives. So obviously one of our goals was to port distributed primitives over to Atomix. And so what is a distributed primitive? It's a cluster-wide replicated data structure or synchronization primitives. So some examples, and distributed primitives, as I think I mentioned before, all have both synchronous and asynchronous APIs to support different programming models. And so some examples are map, set, tree, lock, semaphore, leader election, etc. And a lot of these primitives look really similar to what has existed in ONOS for a long time, but there are some extras also. And so this, again, the API looks really similar to ONOS. It uses a builder pattern. You can get an instance of a builder for a specific primitive type and then configure it. And the same patterns are used for all kinds of primitives. Now, the one thing that's in here is a ... which is what I'll try to fill in through this talk. Yeah, so what? This is all a bunch of stuff that basically was in ONOS so far that's just been moved over to Atomix, and it's not that exciting. Well, so there are two things that differentiate the work that's been done in Atomix from what existed in ONOS in the past. And so number one is configuration, and the second one is deployment. And so I'll talk about each of these and how each of these support the sort of the tenets that I outlined for Atomix. So configuration. So in addition to a code-based configuration, Atomix, it wants to be unopinionated, so it also supports configuration files, right? And so this is HOCON format, which I think it was created for Akka or something. So it's sort of a JSON superset, so you can write configurations in JSON or HOCON or properties files. And the way that fits into the system is, well, going back to the cluster membership service, for example, there are two sort of components to the cluster membership service or to cluster management that can be configured, right? And so there's node discovery and the cluster membership protocol itself. So the responsibility of the node discovery protocol is to essentially figure out how to join a cluster. And I'll show you why this is important. So basically, when a node is bootstrapped, it uses a node discovery protocol to find other nodes to join. And this is a pluggable abstraction. There are different mechanisms that you can use. And this is what makes Atomix able to adapt to different environments. So for example, the bootstrap discovery protocol basically just lists a list of nodes and says, hey, join this existing cluster if you know the node information. Another alternative is multicast. So you can use a multicast discovery protocol, which basically listens on a multicast group for some nodes broadcasting to the group and broadcasting their connection information. And then a third option is DNS. And so this is something that is actually for Kubernetes. So Kubernetes relies heavily on DNS for service discovery, and they add service records to their DNS servers. And so this can be used in Kubernetes to start an Atomix node that can automatically find other nodes to join. And then, so the second component of cluster management is the cluster membership protocol. So basically the cluster membership protocol is responsible for handling everything after you figure out what the initial cluster members are. And so it's responsible for joining a cluster, listening for other nodes joining the cluster, and detecting failures or detecting when other nodes are leaving the cluster. And again, this is a pluggable abstraction that, I mean, you can choose the sort of properties, and I'll show you the different protocols and their properties. So again, this is just something that's configured in a configuration file or in code. And so there are different mechanisms that you can use to configure it. So the heartbeat protocol. So the heartbeat protocol is historically the protocol that was used in ONOS basically for a long time. And basically the way it works is just every node constantly broadcasts their existence to every other node, and failures are just detected by using a timer, right? And so it looks something like this. If you have a 4-node cluster, each node holds membership information for each other node, and they just constantly broadcast messages to each other. And so if a node crashes or wants to leave the cluster or whatever, each of those other nodes has a timer, and they just ultimately eventually remove that member from the cluster. And so this is configured just by using the heartbeat protocol, just by configuring the instance to use the heartbeat protocol. But the problem with this is, say, like in a 5-node cluster, this is basically what's happening all the time. And so this isn't a huge problem in a 5-node cluster, but what if there are 50 nodes? You know, when you add the 50th node, you're adding a heartbeat to 49 other nodes. And so some of the problems with this and we want to future-proof, obviously. So some of the problems with this are that it obviously doesn't scale well. There's a huge growth in network traffic as the size of the cluster grows, and with service-oriented architectures, you have more membership, and so the protocol can explode. And it doesn't handle simple network partitions well, which means more frequent false positives, which we actually have seen a lot, or quite a bit. But the sort of counter to that is that if you're using something like a phi accrual failure detector, then it can detect failures more quickly, which, depending on your use case, could be a good or bad thing. And so the alternative to this that's implemented in Atomix 3 is the SWIM protocol. So SWIM stands for Scalable, Weakly Consistent Infection Style Membership Protocol. I remembered that. Yeah, and so the goal of this protocol is to reduce the load on the network, improve scalability, and reduce false positive, which are all the sort of drawbacks to the other protocol, right? And so rather than nodes constantly heartbeating each other, this is sort of a pull-oriented protocol where nodes just periodically probe each other to see if one of their peers failed. So nodes will constantly just send a message saying, hey, are you alive? Hey, are you alive? Hey, are you alive? Oh, and when a node crashes and a probe fails, there's another step to this where they don't just get marked dead at that point. They also try to find other routes to the node to see if there's something wrong with their network connection or machine or something. And so what this means is that in a simple network partition where the left node just can't connect to the right node, that node still has a chance to refute the fact that it left the cluster or crashed or anything. And this is how false positives are reduced. And then for scale, updates to membership is just gossiped around the cluster. And so this is a much more, and it's just sent over UDP, this is a much more scalable way to propagate information across large clusters. And again, this is just a matter of configuration, right? Just set the protocol to SWIM and then configure it however you want, and you suddenly have a totally different membership protocol. Yeah, so this protocol scales much better. The growth in network traffic is much lower, handles some basic network partitions, and avoids false positives. But the downside is that the way that it actually ultimately marks peers dead requires more time. So there's sort of a trade-off that this is where we start to allow trade-offs where you can opt for faster failure detection or more reliable failure detection. But how does Atomix replicate state then? So there are 3 protocols that Atomix 3 now uses to replicate state. So there's Raft, which it always has. There's a new primary backup protocol, and there's a distributed log protocol, and I'll talk about the other 2. But first, I want to talk about Raft a little bit. So Raft basically it's a leader-based algorithm. In other words, changes go through a leader and are replicated to some backup nodes. And so it allows nodes to be in one of 3 states at a time. So there's a follower state in which the follower receives entries or changes from the leader, the candidate state in which a node is trying to become the leader, and the leader state in which the node is receiving client requests and replicating the followers. So if you look at a diagram of Raft, basically when the cluster starts, all the nodes start in the follower role, and all of them have timers. And these timers are basically they're listening for a leader to send them a heartbeat and say, hey, I'm the leader. If they don't, then their timer will ultimately expire, or one of their timers will expire, and that node will become a candidate. And in the candidate role, the node requests votes from the other nodes. If they vote for it, then it becomes the leader and then starts sending heartbeats to the other nodes. And so while in the leader role, a client can connect to the leader and start sending operations. So what an operation is in this context is think of a distributed primitive. When you create like a consistent map and call put on the map, all that is it's basically turned into a log entry that's replicated inside of Raft. So each node has a persistent log on their disk. So the leader will basically append an entry saying, oh, hey, this is a put operation with this key, with this value on this map. And then it will replicate that to its followers, which then write those entries to their own logs and respond, acknowledging the write. And then once they're replicated to a majority of the cluster, the leader can commit it, and then it applies it to a state machine and returns the output. And so this can happen sort of over and over and over. And so what you end up getting is basically a history of all the state changes in the cluster. And this is how you get persistence through the Raft protocol. Because if the whole cluster goes down and restarts, then all of the nodes still have a full history of all the state changes. And all they need to rebuild the state of the system is to replay those entries and apply them to their state machines. And so when a node crashes, well, another node can just time out, request some votes, and then get elected leader. And so this is a leader-based protocol. And so the reason that I went through that is because I want to point out some similarities in that protocol, between that protocol and the other replication protocols that I mentioned. So the primary backup protocol is sort of like a really simplified version of what Raft does. There are a lot of intricacies to the Raft protocol that allow it to guarantee consistency. But primary backup is sort of a similarly structured protocol, at least. It elects, well, let's look at a diagram of it. So I mean, the diagram for a primary backup looks like this. So the primary backup protocol, as it's implemented in Atomix, uses Raft to elect a primary node. Operations go through the primary. It replicates those operations to backups and applies them to a state machine. But there are some subtle differences that make it useful. So one is that there's no persistent log in this case. So it's just a purely in-memory protocol, which is really the primary overhead of Raft. And number two is that it doesn't require a quorum, or it doesn't require changes to be replicated to a majority of the cluster. So you can do things like you can tune it for low latency. So like you can tell it to replicate only to one backup, or replicate asynchronously to one backup, and get a lot better performance characteristics that way. But the nice thing is that it's structured similarly to the Raft protocol. And so that sort of allows us to build abstractions that can use each of the protocols. And so the same thing goes for the distributed log protocol. So the distributed log protocol is basically just a generic, it looks sort of like primary backup, but it's just a generic protocol for writing a distributed log. And so again, it does leader election through Raft, replicates basically log entries from a primary to some backups. And then, but it has the same sort of replication constraints as the primary backup protocol did, where it can replicate asynchronously or replicate to less than a majority of the cluster. And so those are all the protocols that are currently implemented in Atomix, and they're intentionally similar so that we can try to build towards the idea of using different protocols for distributed primitives. So but the problem with these is they're leader-based protocols, and leader-based protocols don't scale well, right? So the solution to leader-based protocols not scaling well is sharding. So if you look at the Raft protocol again, all writes have to go through the leader, but if you just create 6 instances of the Raft protocol, then you can spread out writes across all of them. And then this is the same image I had earlier, which is that those partitions can then be spread across all the nodes, and you can balance the leaders across nodes and things like that. And so this is the typical way to get scale with these kinds of protocols. And so partition groups are sort of an abstraction for defining partitions or shards, or basically multiple instances of a protocol to run inside of an Atomix cluster. So for example, if you want to run the Raft protocol, you configure a Raft partition group. Primary backup protocol, you configure a primary backup partition group, etc. And partition groups can be they can reside, or partitions can reside on any node just based on its configuration. And this is where we start to get into nodes' roles are defined by their configuration. And this is what a configuration looks like. So if you just add this configuration, a Raft partition group, then this node, the node that's configured with this configuration, is going to be a Raft node. And so what you can do is you can run different protocols on different sets of nodes in the cluster, right? You can run a cluster that's half primary backup nodes or half Raft nodes, or mix them all together, or do whatever you want. There's only one constraint with respect to partition groups in Atomix, and that is that there must be a management group. So the management group is just a required partition group that Atomix uses for basically for managing primitives. So when you create a primitive, it creates a record that that primitive exists and what type it is and what its name is, and et cetera. And then that partition group is used for electing primaries in the primary backup protocols and managing transactions, which is outside of the scope. And then as far as additional partition groups, you can define as many as you want on whichever nodes you want. And so when a node starts and connects to a cluster, it basically discovers its partition groups and thus discovers where data is stored in the cluster. And so this is what a complete configuration looks like, defining multiple partitions. So the management group is defined at the top, which basically says use Raft to store primitive information and manage transactions and manage primary elections, and then create a Raft partition group with 3 partitions and a primary backup partition group with 32 partitions. And then we'll see that primitives can be stored in the data partitions. And again, the same thing can be done in code using the builder pattern. This is a code example of the exact same configuration that was on the last screen. And so on to distributed primitives. So with that, with the protocols defined, basically all distributed primitives are as an interface to replicated state machines run on some arbitrary protocol. So we basically abstract the notion of a replicated state machine, provide interfaces to protocols that allow them to, all the different protocols to manage the same replicated state machines, and client interfaces for all the, a client interface for all the protocols to allow primitives to interact with each of them. Right? And so basically to create a primitive that uses a specific protocol, all you do is provided a protocol configuration. So going back to the ... that I skipped earlier, it's a protocol configuration. And so the protocol basically defines, it defines the consistency model, it defines the throughput and latency characteristics of the primitive. And so this allows us to make significant trade-offs as to how primitives behave. And so these are the components of a primitive configuration. There's a primitive type, the primitive name, which basically the name identifies a piece of state, and 2 primitives with the same name will always reference the same piece of state, which is a replicated state machine. The protocol configuration, which defines what protocol it uses and which partition group it's stored in, and then other primitive configuration. These configurations can also be done in configuration files. And so you can make a map that uses the multi-Raft protocol, which is basically a Raft partition group, the multi-primary protocol, which is a primary backup partition group. And you can see different options. Like in this case, it's configuring a specific number of backups, which couldn't be done in the Raft protocol, and it's also telling it to replicate asynchronously, which definitely can't be done in the Raft protocol. And then you can create one that just reads through a distributed log and creates a client-side state machine. And so what this means is that you can also control where state is stored. So by defining partition groups and then defining the protocols and partition groups that primitives use, if you create a map on a client, you can tell it to store data on some specific nodes using some specific protocol or some other nodes. And so this is how we get, this is what's meant by nodes have no roles, or nodes roles are defined in their configuration. You can, you can architect a cluster however you want. And this is the same for all of the primitives that I went through earlier, right? An atomic counter can use whatever protocol it wants, lock, leader election, etc. There's also a distributed log protocol, which is sort of like Kafka or primitive. So, and that brings me to deployment. So up until now, what we've seen basically is a code-based API to all of these things. But obviously in our architecture diagram for the OWL release, we wanted a separate Raft partition, a separate cluster for ONOS to interact with. And so code is not the only way that you can run an Atomix node. Atomix also provides what we call the agent. And so the Atomix agent is basically just a standalone service or a standalone server with an HTTP API, or which can be connected to over the normal TCP-based communication APIs. And so with all that, like I said, Atomix is unopinionated. You can make lots of different architectures with the configurability of Atomix. Right, you can make client-server architecture where the server is basically an Atomix agent and the client is a stateless Atomix library node. You can make sort of you could run the agent as a sidecar. Remember in the Google talk this morning, he was talking about sidecar containers. You can run the agent as a sidecar to some application written in any other language, and it can use the agent to for cluster membership or for primitives. And then that agent can communicate with wherever the data is stored. Or you can build symmetric clusters like a data grid architecture where every node both stores data and operates on the data by creating distributed primitives. Yeah, so that's basically all of the Atomix 3 stuff I wanted to cover. But how does this fit into the ONOS architecture then? So going back to the diagram that I showed initially, obviously we want to separate the Atomix nodes from ONOS, and so it probably becomes a little clearer what those nodes' roles are. So basically, the nodes on the top are basically Atomix agents, obviously, and they're configured with Raft Partition Groups, and then the ONOS controller nodes connect to them and connect to each other also. So another way you could think of this actually though, so the roles of these two sets of nodes are that Atomix is really responsible for, it provides cluster management and persistent protocols, and then on the ONOS nodes, they do messaging between each other and still in-memory replication protocols, because there are still a lot of eventually consistent protocols that run on the ONOS nodes themselves, like the flow rule store and link store and lots of southbound protocols, or southbound related stores. But you could also think of this as just being all Atomix nodes, because that's what it actually is. So now, since the upgrade to Atomix 3, ONOS is actually just running an Atomix node internally that manages cluster communication for it, manages distributed primitives for it. And so it's really Atomix that's drawing all these lines. And so going back to pre-OWL, the cluster configuration basically looked like this. Again, basically in the cluster configuration, this is cluster.json. You had a list of nodes, and so every node listed every other ONOS controller node that it was going to connect to. And then it also listed a set of partitions. So the change in terms of configuration in this architecture is that, like I said, the Atomix agents are running Raft, so they're configured with Raft partition groups. So actually in the Atomix distribution, there's an example configuration file for ONOS that will look something like this. And so the Atomix nodes will be configured with some discovery protocol, some membership protocol, and then Raft partition groups, which ONOS nodes expect to be there to persist data. And then the ONOS cluster.json has changed a little bit also, and I'll show you why. So whereas it used to list the set of nodes, the controller nodes in the ONOS cluster, now it just lists the Atomix nodes. So you can provide a local information about the local node and then some set of IPs for the remote Atomix nodes to which to connect. And so what this means is that ONOS nodes don't know about each other in terms of configuration. They don't need to. Because what happens is we use Atomix for service discovery in this architecture. So when an ONOS node starts, it only knows about the Atomix nodes, it joins the Atomix nodes. They share membership information among each other and then broadcast the membership changes back down to the other ONOS nodes that existed before. And of course, those nodes have embedded Atomix instances, which also get updated with the membership information, and they connect back to the joined node. And so what this means, this works in both directions. So in the event a node crashes or you just want to remove it from the cluster, the Atomix nodes will know about that and they'll notify the other ones. They'll notify the other ONOS nodes and they'll remove it from the cluster. And so what this creates is a really dynamically scalable cluster. Remember, one of the issues that I mentioned with the pre-OWL architecture was that it was very difficult to resize the cluster, and that's no longer the case because Atomix is used for service discovery. Raft is no longer run on the ONOS nodes, and so you can do this, and we've tested it. You can just kill all but one of the nodes. Yeah, and then the other component of this, and one of the other driving forces behind the architecture changes was for upgrades. So you can now upgrade the Atomix nodes independently of ONOS to introduce bug fixes into a running cluster, and this is perfectly safe and it's tested all the time. And you just do it with a normal rolling upgrade, and in Kubernetes, something like Kubernetes, you can just use a rolling update strategy, and that will update the Atomix nodes, and you thereby get new bug fixes, new features, and things like that. So that's about all I have on the ONOS architecture. So a couple of specific details about the implementation. So currently, ONOS the 1.14 and 1.15 releases rely on Atomix 3.0, and those releases use the heartbeat protocol. So they relied on the old membership protocol. In ONOS 2.0, we upgraded to Atomix 3.1, which introduces the swim protocol, and you can use the swim protocol in ONOS 2.0, which is kind of cool. As for the primitive protocols, so I mean, our goal was to make primitives more flexible and give people options for distributed primitives, but because of future work on next generation ONOS that hasn't been exposed yet, but we're hoping to use it in that work. So that's it. Here's some links for ONOS and Atomix if you want to contribute or look through the docs.
Thanks, Jordan.
Yep.
Any questions? So Jordan, very briefly, the node goes down, and it comes back up. How does it? Oh, sorry. If a node goes down and then comes back up, how does it get the state to replay? You said it replays the whole log, but like if the disk is gone or something and it was a new OS or something,
yeah,
how does that work?
Well, in that case, the technically correct thing to do is to reconfigure the Raft cluster to remove that node and then add another node. But in practice, if you just did that and shut down a node and deleted all the state, when it came back up, it would get the logs from the leader, because the leader basically, there are a ton of details of the Raft protocol that aren't in there, but the leader sends a message and they just resolve the differences between their logs. That's all the Raft protocol does. So the leader sends a heartbeat to the follower sends back the highest index in its logs basically, and then the leader starts sending entries from that point.
Okay.
And so in practice, what would happen is the leader would just send its log. But actually actually what would really happen is the leader would send a snapshot of its state machines and then some of the logs.
Thanks for the nice description of details. I have a question regarding in this 3.1, ONOS generally use application master. Since Raft has moved out, so how those application leaders will be elected because Raft has gone out.
Yep.
So who will do that work? Whether some Raft version will be maintained inside ONOS as well? How that will work?
Yeah, so this is actually a frequent point of confusion, I think, as to, so there are sort of a lot of layers to leadership in ONOS, right? So there's Raft leaders, and then, well, the masters, the device masters. So actually the way that device mastership is managed is through a state machine, a Raft replicated state machine. And so when a node comes up or a device connects and a node tries to become the master, it's actually submitting an operation to some Raft partition saying, try to become the leader for this device. And it's the state machine that controls mastership elections. So if that state machine is running on some other set of nodes, it's actually a client that's communicating with the state machine that's managing mastership elections for the controller nodes.
Another question that I have regarding this cryo.
Yep.
So basically there are many problems when, let's say, you store the state and then you somehow uninstall the, basically reinstall the new version of application or something like this.
Yep.
And though you have not changed the classes that has been stored,
Yep.
even if even after that the data that has been stored does not comes up, there is exceptions like class loader has been.
Yep.
So how to mitigate those problems? Basically those are required when you are doing the development testing, or even in some basically deployments, you want to change the application. At that time some data is there, you want to bring new application with that data.
Yeah, so Cryo does have some features for handling changes to the schemas of objects. So they have alternative serializers, and there's actually an API in the ONOS serializer API, or the Cryo namespace API, that allows you to enable compatible serialization, which it will write field names and use that to ensure both backwards and forward compatible serialization. So an old node can read data from a new node, and a new node can read data from an old node. But Cryo is still problematic in this respect, and that's why we're switching to protobuf ultimately.
Sorry?
Cryo is problematic in that respect, and that's why we're changing to protobuf eventually. So okay. Protobuf has a lot better features, and it's built into the schema language for handling this problem.
Okay, thank you.
Just one quick final question, Jordan. In terms of the practical deployment of this, of we'll say an ONOS cluster, then, I mean, what would be your recommended, scale? Would you be talking about 3 physical machines for the Atomix nodes, and then say, like you showed in your slide, 5 ONOS nodes?
Yeah, I think that's a good one. So there are a couple. People actually have asked this a few times recently. So the one thing that you definitely do want is for any nodes that are running Raft partition groups to be running on separate physical machines. Because if 2 of them are running on one physical machine, that machine goes down, you lose a majority of the cluster. And then your cluster goes down, basically. So you definitely want to try to balance the nodes that are running those important protocols across multiple points of failure. But as for the other nodes, yeah, I think for the ONOS nodes, I think 5 is a pretty typical number. We test them frequently up to like 7 or 9.
Right. Okay. In your upgrade scenario, I think it was 2 slides back or something like this, you were talking about, yeah, with this one, go back 2 steps from this maybe. Yeah, even when it's white, when the third one is white there, I mean, are you in a situation that if one of those went down, those green ones, you're in a split brain scenario? Yeah.
Yes, you definitely are.
Okay.
Yeah,
Is
so,
there any facility for a witness service or anything there?
So the problem is that Raft, so the problem is there are a lot of weird details about the Raft protocol that make it difficult, especially with sharding, to just move nodes around or reconfigure the size of those green nodes because they're running Raft. We haven't implemented, so we're actually working on a protocol to allow for that, but it's complicated because if you have a Raft partition group with 3 partitions running in it, and you want to reconfigure it to add a 4th node or something, you have to also reconfigure all the partitions at the same time and make sure that that's an atomic operation. And so you have to run like a 2-phase commit protocol across it. So basically you're doing consensus on top of consensus to make sure that either all the partitions are reconfigured to add a new node or none of them are reconfigured. And so there are a lot of weird details to doing things like that. But I think probably in 3.2 that would be implemented too, because that's really important just for allowing scaling also of those nodes. Currently there's no way to scale them. Okay, thank you.
All right, thank you.